Welcome to Week 4 Summary for the online course Fundamentals of Electronic Materials and Devices. Starting from this week, we will mainly focus on electronic devices. In any device, we put together two different kinds of materials. When that happens, we say that a junction is formed, and at equilibrium, the Fermi levels of the two materials tend to line up. We will mainly look at three types of junctions. We will look at metal-metal, metal-semiconductor, and finally semiconductor-semiconductor junctions. In this week, our focus would be on the first two, and we will start briefly to look at semiconductor junctions at equilibrium. We'll also only look at ideal junctions. So these are junctions which have a perfect interface with absolutely no defects. In practice, this is not completely true, but we will use the ideal junction for us to understand the physics behind how semiconductor devices work. So let's start with metal-metal junctions. So in this particular case, we have platinum and molybdenum as examples. So before the junction is formed, the Fermi levels of both the materials are different, simply because their work functions are different, but the vacuum level is same. When we put platinum and molybdenum together to form a metal-metal junction, we say that at equilibrium, the Fermi levels line up. One way to understand this is to say that electrons from molybdenum, which are at a higher energy level, move to platinum to occupy all of these empty states. So at equilibrium, the Fermi levels tend to line up. Because electrons move from molybdenum, we have a net positive charge on the molybdenum side, while because electrons move towards platinum, there is a net negative charge on the platinum side. These charges are located at the surface, and we say that there is a contact potential, and the contact potential is equal to the difference in the work functions of the two materials. Metal-metal junctions are useful in the case of thermocouples. They're primarily used to measure temperature. They work on the principle of the Seebeck effect, which says that if I have a single metal, one end of which is hot and the other end of which is cold, there is a voltage difference simply because at the hot end, the electrons have a greater mobility than the electrons at the cold end. So if I have a single metal, there is a voltage that is developed, which is called the Seebeck potential, and this is proportional to the temperature difference, and the proportionality constant is called the Seebeck coefficient. This Seebeck coefficient is different for different metals. In the case of a thermocouple, we use two materials with different values of the Seebeck coefficient, so that there is a junction potential that is developed between the hot end and the cold end. By careful calibration of these junction potentials, we can use these thermocouples in order to measure temperatures for a variety of different systems. So moving on, we will look at a junction that is formed between a metal and a semiconductor. We will first consider N-type semiconductor, and then we will move to P-type. So if we have an N-type semiconductor and we have a metal, if the work function of the metal is greater than the work function of the semiconductor, we say that we have a Schottky junction. On the other hand, if the work function is less, we say that we have a ohmic junction. So let us now look at a Schottky junction. So here is the metal where phi m is the work function of the metal. Phi n is the work function of the N-type semiconductor. So remember, this is N-type. The Fermi level is closer to the conduction band than to the valence band. So when we form a junction, we apply the same rules as before, that the Fermi levels must line up. Electrons in the N-type semiconductor, which are at a higher energy level, will tend to go and occupy all of the empty states in the metal, So electrons flow from the semiconductor to the metal. This means there is a contact potential. So remember, when electrons flow, this side is positive, this side is negative. There is a contact potential, and there is also a depletion region in the semiconductor side. So this schematically illustrates the formation of the contact potential. The electric charge in the metal side is much larger than the semiconductor side. So on the metal, the negative charge is at the surface, but in the semiconductor, the charge extends to a particular region inside the semiconductor, and this region is called the depletion region. So the region is depleted of the electrons. We only have the positively charged donor ions. That is why it's called a depletion region. So we say that at equilibrium, the bands bend on the semiconductor side, and the convention is the bands bend up in the direction of the electric field. So we can now draw the equilibrium band diagram for the Schottky junction. So the Fermi levels are aligned on both sides. We have a depletion region in the semiconductor. The electric field goes in the direction from n-type to the metal because this is positive, this is negative, and bands tend to bend up in the direction of the external field. So there is a contact potential, which is nothing but the difference between the work function of the metal and the semiconductor. And we also define something called the Schottky barrier, which is nothing but the work function of the metal minus the electron affinity of the semiconductor. The Schottky barrier is the barrier that an electron has to overcome if it wants to go from the metal to the semiconductor. Now at equilibrium, when no bias is applied, the Fermi levels line up, but when we apply an external bias, the Fermi levels are no longer equal. We can apply two kinds of bias. The first is called forward bias, in which the metal is connected to positive. The n-type semiconductor is connected to negative. In this case, the external potential tends to oppose the built-in contact potential. So this means the overall potential is reduced. It is V0 minus V external. Now the potential is the barrier that prevents electrons going from the semiconductor to the metal, which means if I reduce the barrier, more electrons can transfer, which means we have a current that can flow, and the amount of current flowing is directly dependent on the external potential that we apply. In the case of reverse bias, the situation is inverted. The n-type semiconductor is connected to positive, metal is connected to negative, which means the external potential is in the same direction as the built-in potential. So the barrier actually increases, and so we have very little current flow in reverse bias. So if you look at the IV behavior of a Schottky junction, we see that in forward bias, the current increases exponentially with the applied voltage, and we write this in terms of current density, where J is equal to J0 times an exponential dependence on the applied potential, and J0 depends upon the Schottky barrier of the junction. In reverse bias, the current is more or less constant, and it is a very small value, and the value is equal to J0. Thus, a Schottky junction acts as a rectifier in which it conducts current only in the forward bias side, but does not conduct or have very low conductivity in the reverse bias side. We saw an example of a Schottky junction with an n-type material. We can do the same with a p-type material, except now the values of the work functions are reversed. So if phi m is less than phi of semiconductor, we get a Schottky junction, and if phi m is more or greater than phi of the semiconductor, then we get an ohmic junction. Let us now look at an ohmic junction and we will again use an n-type semiconductor as an example. So remember, in this case, the work function of the metal is smaller than the work function of the semiconductor. So now we have electrons from the metal go into the semiconductor. So instead of a depletion region, we have an accumulation region at the junction. So a ohmic junction essentially behaves as a resistor. So in both forward and reverse bias, we have a straight line IV curve. There is no rectification. And a Peltier cooler actually works on the principle of using ohmic junctions. It will basically either release heat or absorb heat depending upon how it is biased. We will now look at a junction which is formed between two semiconductors. So one of the semiconductors is p-type, the other is n-type, but they are both based of the same semiconductor material, which means the underlying semiconductor is the same. Only one of them is p-type, the other is n-type. Such junctions are called homojunctions. So for example, we can have silicon where I form a junction between p-type silicon and n-type silicon. So again, before the junction is formed, the Fermi levels are separate. The n-type semiconductor has a Fermi level closer to the conduction band, while the p-type semiconductor has a Fermi level closer to the valence band. When we form a junction, we say that the Fermi levels must line up. It's equivalent to saying that extra electrons from the n side move to the p side, while extra holes from the p side move to the n side. These two are essentially unhighlighted. So we have a region at the interface where we don't have charge carriers, but we only have positively charged donors and negatively charged acceptors. This region is called the depletion region, and there is a contact potential that is developed across the p-n junction. This contact potential depends upon the concentration of Na and Nd, which is nothing but the dopant level in the p and n type, and Ni square, where Ni is the intrinsic carrier concentration. The depletion region, some of it is on the n side, some of it is on the p side. The total width is nothing but Wn plus Wp, and by charge neutrality, we can show that the width of the depletion region is inversely proportional to the concentration of the dopants. So if Na is larger than Nd, Wp is smaller than Wn, and vice versa. So with this week, we look at p-n junctions at equilibrium. In the next week, we will see what happens when we now apply a bias to a p-n junction, and we will see what happens in both forward and reverse bias. Thank you.